Welcome to the pre-recording of the second half of lecture 8 of computer algorithms, scheduled for the end of the third week in an 8-week course. We will introduce divide and conquer algorithms by a geometric problem, finding the closest pair of points in the plane. Here is the straightforward approach. We have endpoints in the plane. We want to compute the minimum distance. So here you see the formula for the distance based on the coordinates of the points P and Q. Essentially, we consider each and every pair, except if the 2 points are the same, but we compute the distance for each pair and we compare this to the minimum distance. So this is a prototype algorithm for a quadratic running time. So observe that if you have compared the first point with the second point, you no longer have to compute the distance with the second point to the first point. So you can actually cut half of the steps, but that would still give you a worst case running bound, so a worst case upper bound of n square. So we can do better by applying the principle of divide and conquer. And we will see that if we apply divide and conquer, we can solve this problem in time n log n. So this is, if you like, computing the minimum distance between 2 points, is therefore a little bit similar to sorting a list of n points. So this problem is also close to the area of computational geometry. All right, let me introduce the idea of divide and conquer with an example. So here you see 21 random points. Why 21? I needed a point in the middle. So we sort the points on their x-coordinates. We have green points and red points and one point that is white that stays neutral. So that point defines the split. Then what we will do is that we will compute the minima of the first half, so compute the smallest distance between all points in the first half. Then we do this same split essentially again on the points in the second half, and there we compute also the smallest distance. So then we have two distances, we call them delta A, delta B, and the smallest distance is then here for this case the smallest of these two distances. So here is the beginning of a recursive algorithm. So we state the problem again. We sort the points. So if there are 2 points with the same x-coordinates, then we use the y-coordinate to break the tie. Either the highest point come first or the lowest point come first. Doesn't matter which convention. We output the minimum distance between the closest pair. So in the base case, if we have 3 or fewer points, then we will start comparing the pairs. It doesn't really matter then. If in general the number of points is larger than 3, we will split the sequence of points sorted on their x-coordinates. So the ones to the left go to A, the ones to the right go to B. We apply the same recursive idea again to both sequences, but then there could be, and here is actually the reason why there is still something missing and why this is the beginning. So every divide and conquer algorithm runs like this, but then there might be something that needs to be done in between. So we have the two halves. Could it not be for this particular problem here that the closest two points lie very close to that splitting line? So could there be um, points that are closer to each other, closer than the points in the first half and points in the second half? So that is where we will focus our attention for the remaining part on solving this problem. So here we have the notation again. Delta A is the minimum distance for the closest pair in the first half. Delta B is the minimum distance of the closest pair in the second half of our problem set. Then we have the little delta, which is the minimum. Now, if there is a point, so it could be that that is the minimum distance, but if there is a point A and Q that are lying and they are in two different sets now, then if their distance is smaller than delta, then they have to lie both within distance of delta of the separating line. So geometrically, if you have a strong geometric intuition, this seems obvious, but it requires rigorous formal proof. So let's make this proof here. So what it means to be that P and Q are less than delta, it implies that their x-coordinates are less than delta. Obviously, the most extreme part is that they have the same y-coordinate, and if their x-coordinates are farther apart than delta, then their total distance cannot be. Okay, so we have that the x-coordinates are less than delta away from each other. This is another way of expressing here. Q is in the right half, so Q minus P, their x-coordinates are positive. Now, if the x-coordinate of the x-coordinate of the separating line is given by L of x, then the L of x must be in between. And we can therefore derive that the difference of that x-coordinate of the separating line to the x-coordinate of the first point P in the left half, because L of x is less or equal than Q of x, then it means that P has to lie within distance delta from the separating line, and we apply a similar argument to show that the second point in the right half must also lie within the distance delta. Okay, so then we have now actually three cases. We have the first half, the second half, and then we have the strip of points that are lying within distance delta. Okay, so this is the definition of this strip S here. So the set S contains all the points in our original point set where the x-coordinate lies within distance delta from the x-coordinate of the vertical separating line. Okay, so now we can solve the problem. So we have taken the minimum delta to be the minimum of the points of the closest pair in the left half. closest pair in the right half. If we actually have now the 2 points in that strip, so if there are 2 points that are of distance less than delta in that entire set, that's either in the first half, either in the second half, or within that strip. Okay, we need to search through the set S, so the algorithm is clear. You search in the first half, second half, and then in the strip. However, what if that strip is now just as large as the entire point set? Then actually the divide and conquer will not have helped you anything. So let's now see that this cannot be the case, and that's actually the part that requires most of our attention. So if we consider, so we have this delta, which is the minimum distance, we can partition the strip around the dividing line in squares. Squares where the length of the sides is the delta of 2. Why is that the case? Because this will make that every square can obtain at most 1 point. So this is important. So as we will derive in the theorem. So the theorem leads to this partition. So the formulation of the theorem is such that you should already have seen part of the proof. So if there are 2 points that are closest than distance delta from each other, then there must be within 15 positions from each other in the strip in the list sorted on the y-coordinate. So inside the strip, we're going to sort the points on the y-coordinate, and we're going to say something about the distribution of the closest points there, how many points we can actually expect. So it's clear that in this strip we only consist, that's the definition, in this strip we only consist this range of delta. And we consider 2 points in the strip, and those 2 points actually, if their distance is less than delta, they're actually within 15 positions of each other. Okay, so let's make that formally. So perhaps I should draw a little bit. So the first thing is that each of these boxes in the partition we can identify with 1 point. Suppose that there would be 2 points in the same box. So we have here the first box. So suppose that we have 2 boxes, 2 points in the same box. The length of the square is delta over 2. Then the distance between the two is actually the furthest they can be apart would be their diagonal. And that diagonal is here. So, but we actually assume that the delta is the minimum. So the minimum of delta A. So I started drawing 2 points in a box in the left half. Well, this delta here is smaller. So we cannot have 2 points in the box. So we can have at most 2 points there. And the S and the T, we can actually assume that S belongs to the left half and t belongs to the right half. So we have now, so the first sentence here makes clear what we mean by a position in this strip. So you can identify one point with every box. Now we can label these boxes. So 0, 1, 2, we have 16 boxes for 15 and 16 in total. So if we have that, so we have now, perhaps I should change color, or let me draw here. So if that now, suppose we start counting, this is box 0. So we have one point here and another point there, and we consider their distance from each other. Now, if there are within 15 positions from each other, we could still have that the distance might be less than delta, but if there is more than 15 positions, so if you move this point here below, then the distance here would start to be larger. And actually it is very crude bound, so if you start by making diagonals, you can actually see that the 15 is a little bit of crude upper bound. So we started by reasoning within the same half. So 3 rows away, here we have this square, so 3 times larger than delta over 2 is larger than delta. So that means that 2 points that belong to the strip, if their distance has to be less than delta, then there are within 15 positions of each other in this strip, sorted on the y-coordinate. So this is a very important observation. In some sense, the book calls it amazing, and it's not at all obvious when we started that our algorithm would work. The next exercise, and that's actually the first exercise in the second half, allows you, invites you to make it three-dimensional analog. Suppose you would be thinking about points in tree space, and you would want to know what is the distance, the smallest distance between any pair of points. There are obvious applications of this. So can you formulate a generalization of the theorem on the previous slide? And can you also prove it? So the purpose of this exercise is to show that you understand the proof of this important theorem. Okay, so now we can do the combination step. So we have computed delta as the minimum of the distances in the first half and in the second half. With this delta, we define the strip. So we collect all the points that are within distance. And then the set is sorted on the y position. So when we are scanning for every point in the set S, we look for another point T in that S, but we only need to look for the next 15 positions to find the candidate for the next point closest to S. So this is the important step that needs to be added as the subroutine to the beginning of our general divide and conquer principle. So we apply the theorem here. So this is in designing an algorithm where we analyze already the properties of the input set. Okay, the algorithm is correct. The beginning of the algorithm, so the total algorithm consists of closest pair combined with closest pair combined, will be correct, and we will prove this by induction. The base case is by comparing the pairs, no point there. So then we state the induction hypothesis. We assume that the algorithm is correct for all point sets of size k, strictly less than n. And then we have to prove the correctness for a point set of size n. So we apply the hypothesis on both halves. So this actually means that both halves are less in size. So we do have the correct smallest distance delta A and delta P. And then we have the combination that returns the delta S for the points in the strip. So therefore, this induction proof shows that the algorithm will give us the correct closest distance, the minimum distance between the points in P. Okay, now why did we go through all the trouble? Because the combination, and I should have pointed this out in when I was phrasing the beginning. So it looks like it is a quadratic step, but it is not, because for every point in the set, we will consider as most 15 other points when we are computing the distance between the 2 points. So the number of operations per point S is therefore constant. So we don't have a quadratic, but we have a linear combination step. And we therefore have the n log n running time, because we can apply the theorem of merge sort, which we have proven rigorously in the first half of this lecture. And that concludes the main result, that we can compute the minimum distance between 2 points of a set of points in the plane by divide and conquer in the time that it takes to sort them. So in various stages we were actually sorting. We were sorting on the x-coordinate, and we were sorting also on the y-coordinate. But this sorting time is actually absorbed in the total running time. Okay, that was the first problem that we solved in the second part. Let's now go to a problem where divide and conquer will give us subquadratic time. And we will look into the multiplication of integers. And I said earlier in this lecture that an integer is not restricted to a machine integer, so we do not consider the bit complexity when we consider the input size. So we idealize our input. We can have arbitrarily long integers, but of course this is kind of unrealistic in practice. We are restricted by machine size. And what if you would now store, so you would implement multi-precision arithmetic, where you have every number, so here we have the number a, that is represented as a sequence of numbers where here actually this is for the bits that we are multiplying. So since we have the base 2, we consider the multiplication bitwise. And here you see the definition of these multiplication. So in a multi-precision arithmetic, instead of 2, you would have 2 to the power 32 if you have working with 32-bit hardwares, or you would be working with 2 to the power 64 if you work with 64-bit arithmetic. Here actually the A subscripts and the B subscripts are just bits. You have multiplied numbers in the elementary school. And this is another typical example of a quadratic time. I'm not writing the algorithm down. So in solving exercise 5, you will start with a formal description for the algorithm in pseudocode. And indeed show that you do have n square worst case upper bound. Okay, we can do better by applying divide and conquer to these two n-bit integers. So we divide their bit sequences in half. We have the highest order bits, A1, B1, and then we have the lowest order bits. We multiply, so here you see the multiplication. So this goes down recursively until the bits, the components of the highest order bits and the lowest order bits are reduced to one sequence. So in step 2 here, we are rephrasing the multiplications now. The multiplication of the largest number can be done by the multiplications of lower numbers. So we have replaced 2 n-bit number multiplications by 4 multiplications of numbers half that size and 3 additions. So the addition costs, so this is all linear in the number of bits, as should be obvious. You have a carry over, but that's just one constant addition at most. Okay, we will solve the recurrence by plain unrolling. So we have the recurrence that to multiply 4 n, so one n-bit number, is bounded by multiplying 4 numbers of half that bit size, and then the addition takes a linear time. So we are counting the number of operations at each level, and we see that the recurrence, we could do this with recursion, but we will do this by plain evaluation of this bound here. So we can see that based on the number of levels, the number of work we do at each level is actually the additions. So we are adding up, and each time we do actually 4 times, but we have the constant 2 that's coming in. So let's work this out. And it turns out that the sum is a geometric sum. We know the formula for the geometric sum. It is applied here. And you can see it's kind of a disappointment. We have done quite a lot of work already and gained nothing. So if you do this in a straightforward divide and conquer, you have no improvement. So this will be a divide and conquer where you need to be a little bit more careful how you divide. So in the previous application of divide and conquer, we had to be very careful how we combine. Here the combination is just addition, but it was the splitting in 4 that was done very carelessly. Okay, so let's redo it then. And here comes the idea attributed to Karatsuba. So if you look at the multiplication again, with the highest bits separated from the lowest bits, then you can get away with 3 multiplications. So how come? Well, you have the highest bits and the lowest bits that you have to do separately, but you can actually, from the total product here, you can subtract the cross products. So that means that you do one product where you add up. So these are 2 additions again. You add up the lowest bits with the highest bits. Seems kind of odd. You multiply those. That will give you something that is too large, but you subtract from this A naught B naught, what you have already computed as the product of the lowest terms, and you subtract the product of the highest terms. So, and this is a proper thing to do because the size of the numbers is actually n over 2, eventually plus 1 extra bit. Okay, 3 multiplications or 3 recursions will actually give you the same result. So instead of having now 4 multiplications on numbers that are half the size, we now do 3 multiplications on numbers that are half the size. Okay, the algorithm is then very neatly summarized in this pseudocode here. You split highest bits from lowest bits, and now the recursive multiply, essentially this is only the recursive part. The obvious case here is when you get less than your size of your numbers is within the machine integer bits, you can do the multiplication then. So it's an induction, it's a recursion step with the base case that involves multiplication of bits here in this mathematical formulation. So we will show that if we are unrolling the recursion that we get at a subquadratic time. So a subquadratic time is where we have a power of the input size that is between 1 and 2. So 1.59 is the approximation for the bound. Okay, so let's do this. So we are unrolling the recursion. We are multiplying 3 numbers of half the size. And we do then a constant number of additions, a number of additions that each costs C. So based on this tree representation here, we can formulate directly the sum of all the operations over the depth of the tree, which is again 2 log of n. The ratio is now not 4/2 as last time, but it is 3/2, which kind of shows the 1.5 coming in. So it's not really the 1.5, it's 159, and then a lot more, as we will see. But this is the start of the proof of the upper bound on this Karatsuba multiplication. All right, we remember again how to work with geometric sums. So we have the logarithm of n that appears in the exponent. Now the base is 3/2, so we can apply the properties of logarithms to make sure that the n does actually not appear in the bound, so we can swap the base with the exponents. Then we do the logarithm of this 3/2, and there is where we have the 5.9. We are satisfied with 2 places of accuracy here in our subquadratic running time. Okay, I hope this explanation helped in understanding better how to apply divide and conquer. In divide and conquer, we have to decide how to split it up. In the Karatsuba case, it was that required most of our attention. So if we don't split up in the right number of sub-problems, it may go badly. Observe that there is a similarity with the other problem where we split it in 2 halves, but then we had a strip to consider. There our attention went into the combination stage. So we had to analyze the size of that strip, making sure that our combination time was not quadratic. Okay, we started a new chapter in our textbook. The main goal of this lecture is actually that you can start to read the textbook, and that is then also the recommendation I conclude this lecture with.